Hello students, welcome to our lesson today. I'm your teacher Alice, and today's lesson we continue looking at the Form 3 second topic, that is the mole. And today what we are going to look at is what we call the empirical formula. The empirical formula. So we start by defining what is empirical formula. And we say empirical formula of a compound is its simplest formula. It is the simplest whole number ratios which atoms of elements combine to form the compound. So we define the empirical formula of a compound as the whole number ratios which atoms of elements combine to form the compounds. Then we say that empirical formula does not necessarily reflect the actual number of atoms in that molecule. So sometimes we give the number into whole numbers if it is a decimal, or we multiply by a particular number to make it a whole number. So that's why we say that the formula does not necessarily reflect the actual number of atoms in a molecule. Then there are some important points we have to note here. We say that the empirical formula is independent of the molecular mass. We are going to see that and how it occurs. Then the empirical formula gives the simplest ratio of atoms in a compound. And also the empirical formula may or may not be the same as the molecular formula. This depends on the actual arrangement of the atoms in the molecule. So it is not necessarily the molecular formula to be the same as the empirical formula, although at times it occurs that the two are the same for a particular compound. So we have these four steps that we use to find the empirical formula given a particular question. We can follow these steps to find the empirical formula. So step number 1, we determine the mass of each element in the compound. At times we are given the mass in grams, and also sometimes we are not given, or we are given the percentage. We have to determine the mass. So the first step, you have to have the mass of each element that is making that compound. Second step, we have to convert that mass of each element into moles. So we pick each element in that compound, its mass, we convert it to moles. How do we convert mass to moles? So we use that formula where we have moles is equals to mass over molar mass. So we shall be taking the mass that we have here in step 1, then dividing it by the molar mass, which we know the molar mass of these elements. So to get the moles, we shall be using mass over molar mass. Step number 3, we are going to find the ratio of moles of each element. How do we do this? By dividing by the smallest number of moles to get the whole numbers. So we take the moles, we check from the moles now from the second step, and we look for the smallest number of moles, which we are going to divide it through all the other moles. Okay, so we are going to see how that is done. Then next step, we are going to write now the empirical formula using the whole numbers here and the chemical symbols for these elements. So the last step is to combine the symbol and the whole number with the corresponding element. Then we say, practically, the empirical formula of a compound can be determined using these examples that we are going to use below. So let us look at these examples. Okay, example 1, we are told to find the empirical formula of a compound with mass 12 grams of carbon. So this compound has 12 grams of carbon and 4 grams of hydrogen. So we are determining the empirical formula. This is a compound that contains carbon and hydrogen, and we call these compounds hydrocarbons. So we have the solution as indicated below. The first step is to determine the mass of these elements, and in fact, we should start by writing the symbols for these elements. So we can write these symbols here. We have carbon, its symbol is C, and then we have hydrogen like that. So we can write the symbols as I have indicated there. Then their masses, determine the mass of these elements. We are already given the masses. So we are told the mass of carbon is 12. So below carbon, we have 12 grams. And below hydrogen, we have 4 grams. So this is mass in grams. The second step, we are going to convert this mass to moles by dividing mass over molar mass. So as we know, the molar mass of carbon is 12, the molar mass of hydrogen is 1. So the next step is to get the number of moles. So for carbon, we are going to take 12 divided by 12, so mass over molar mass, to give us 1. Then that of hydrogen, we have 4 divided by 1, which is 4. So we have the moles now, 1 and 4. The mole for carbon is 1, and that of hydrogen is 4. So these are whole numbers. So the last step is now to combine the symbol with its number or its ratio, so that we have carbon has a ratio of 1, so we don't have to indicate that one, and then hydrogen has ratio 4. So the compound has the empirical formula CH4. That is how simple we calculate or we find the empirical formula of compounds given the mass. Okay, so the empirical formula of that compound is CH4, and we call that compound methane. Example number 2, we are given that a compound contains 18 grams of carbon and 6 grams of hydrogen. So we are supposed to find the empirical formula of that compound. So we repeat the same procedure. We have carbon and hydrogen. So this is also a hydrocarbon. So we see that the symbol for carbon is C and that of hydrogen is H. So the first thing we look at or we determine is the mass, and we are already given the mass of the two is 18 and 6 respectively. So we have now to calculate the number of moles. So to calculate the number of moles, this is where we are taking the mass, we are dividing it by the molar mass. So that mass of carbon was 18, its molar mass is 12. So 18 divided by 12, that is 1.5 moles. Again, the hydrogen present in that compound has a mass of 6 grams. Then its molar mass is 1 grams per mole. So we are dividing 6 divided by 1, which is giving us 6 moles. So the next step, we look at the smallest number of moles. For our case here, the smallest number is 1.50. So 1.50 is going to divide through the moles of carbon and hydrogen. So we take To get the smallest number of moles, we divide 1.50 divided by 1.50. So that is for carbon. And that of hydrogen, we found it is 6 moles. We divide by the smallest number of moles, that is 1.50, to give us 4. So again, now we can combine carbon, that is C, with 1, and hydrogen has a ratio of 4. So this one will be CH4. So that is also a hydrocarbon, and that is the formula. So these 4 here represent the number of atoms in the number of hydrogen atoms in that compound. So you can see how it is easy to get the empirical formula. So as long as you have the mass, you get the moles by saying mass over molar mass. From there, you pick the smallest number of moles and divide through those other moles, whether they are 2 or they are 3. They can be more than 2. It is not necessary we have a carbon and a hydrogen. They can be more than that. Then after dividing, we get the ratios. It should be whole number. If it is not a whole number, we should check whether it is close to a whole number, we round off. But if it is not close, like for example 1.5, that is when we multiply by a certain number that will make the smallest number that can make that decimal a whole number. So that is how we are calculating our empirical formula, and then the ratios, and then we combine with the symbols to get the formula itself. Let us look at example number 3. So example number 3, we are given that a compound consists of 40% carbon, 6.67% hydrogen, and 53.33% oxygen. We are told to find the empirical formula. So here we are not given the masses, but we are given the percentages. So the first thing is to determine the mass. And how do we determine the mass of these elements? We assume a convenient mass. For example, I used 100 grams to be my convenient mass. So the carbon will be 40% of this 100 grams. So 40% of this 100 will be 40 grams. Then that of hydrogen, its percentage composition is 6.67%. So 6.67% of 100 will give me 6.67 grams, while that of oxygen, which is 53.33% of 100 grams, will give me 53.33 grams. All right. Now I have my masses. Now I'll go to the next step by finding the number of moles of each element. I start with carbon. So we know moles is equals to mass over molar mass. So that is mass of carbon is 40, its molar mass is 12 to give me 3.33 moles. Hydrogen has 6.6 grams, that is its mass. Its molar mass is 1, so giving me 6.67 moles of hydrogen, while that of oxygen is 53.33 grams divided by its molar mass, which is 16 grams per mole, to give me approximately 3.3 moles. The next step now will be to find the smallest number of moles. The smallest number of moles, as we can see here, is 3.33, which belongs to carbon and oxygen. Okay, so 3.33 will be dividing all through. So we divide here by 3.33 to get the smallest number of moles. So divide by 3.33, divide by 3.33, divide by 3.33. So carbon will have a ratio of 1. Hydrogen will have a ratio of 1.983, that is 6.67 divided by 3.33. So that will give me 1.983 approximate. It is an approximate. Then oxygen 3.33 divided by 3.33 will give me 1. So the ratio now will be 1, the other one will be 1.983, and the other one will be 1. But we said these ratios must be a whole number. So this 1.983 we have to convert it to a whole number. Therefore, how do we convert this to a whole number? By rounding off. It is close to the whole number. It is close to 2. So instead of multiplying, now we can only round off to get 2 here. That is why we are saying hydrogen has a ratio of 2. So now we can combine these elements using the symbols and the ratios. So we can see that carbon, its symbol is C, so it corresponds to ratio 1. Hydrogen H corresponds to ratio 1, and oxygen hydrogen has ratio 2, so it corresponds to 2, and then oxygen ratio 1, it corresponds to, so O corresponds to 1. So the formula will be CH2O, and that is the empirical formula of that compound. So that is our example 3. So now let's move to our example 4. So next question. This was an experiment where magnesium was burnt in air and the following results were recorded. So when magnesium was burnt in air, we used an empty crucible and a lid, which we measured to be 19.52 grams. Then the mass of crucible plus lid plus the magnesium we are burning was giving 20.36 grams, and the mass of crucible after burning, so plus magnesium oxide plus the lid, was giving us 20.92 grams. So we were required to find the mass of magnesium, the mass of magnesium oxide, and the mass of oxygen. So to calculate the mass of magnesium, we were taking the mass of the crucible plus lid plus the magnesium. Then we subtract the mass of the empty crucible plus lid. So this is what you are doing. So the mass of crucible will subtract the mass of crucible, lid minus lid. So we are going to have magnesium. So this was 20.36 subtract 19.52, and this was giving us 0.84 grams. So that is how we came up with the 0.84 grams mass of magnesium. Then mass of magnesium oxide, this is where we were taking the mass of crucible plus magnesium oxide plus the lid. We subtract the mass of crucible plus lid. So that will give us the mass of magnesium oxide. So that was 20.92. We were subtracting 19.52. So this was giving us 1.40 grams. This is what we have here. Then finally, calculating the mass of oxygen, we were taking the mass of magnesium oxide minus mass of magnesium. So that was 1.4 grams subtract 0.84 grams. So that was giving us 0.56 grams. So mass of oxygen was 0.56 grams. So the question was, from the empirical results given above, determine the empirical formula of the compound formed when magnesium burns in oxygen. So the compound formed when magnesium burns in oxygen is magnesium oxide. So we are given the mass of magnesium to be 24 grams and that of oxygen to be 16 grams. So let us see how we are going to calculate the empirical formula of magnesium oxide in this experiment. So what we start with is by writing the element. We show the elements that we have. So the first row here, we are going to have the elements. So the elements, we have magnesium, and we have oxygen. So magnesium and oxygen are our elements. Then from our results, before we go to the results, we get the symbols for these elements. So for magnesium, the symbol is Mg, and for oxygen is a capital O. So from there we look at the mass. So what is the mass of these elements? So the mass of magnesium, we had it is 0.84, and that of oxygen was 0.56. Okay, the next row we are going to have the what? The molar mass. So the molar mass of this element, so molar mass. So molar mass for magnesium, we were given it was 24, and that of oxygen is 16. So whether you are given or not, you should know, or you should be in a position to know that the molar mass for magnesium is 24 and that of oxygen is 16. So from the previous examples, whatever was following when we have the mass and the molar mass is to calculate the number of moles. So the next step, we calculate the number of moles. So the number of moles will be mass over molar mass. So that is 0.84 divided by 24. And this gives us 0.035 moles. That of oxygen will be 0.56 divided by 16, which will also give us 0.035. So those are the moles. So to get this, the smallest number of the moles, we have to get the mole ratio. We divide by the smallest number of moles, which is 0.035. So we are going to have here 0.035 divided by 0.035, which will be 1. Then also the same for oxygen. It has 0.035 moles divided by 0.035 to give us 1. So the ratio for oxygen is 1, that of magnesium is 1. So whatever is remaining is to write the elements with the mole ratio that will give us the empirical formula. So we write our symbol for magnesium here. Its corresponding ratio is 1. So here we have 1. We said we don't write 1. Then that of oxygen, it has a mole ratio of 1. So that is 1. So the empirical formula of the compound formed when this magnesium was burnt in oxygen was this compound that we are calling magnesium oxide. And from Form 2 work, remember when you are looking at the chemical formula, we were taking, for example, magnesium, its valency is 2, and oxygen, its valency is what? Is 2. So if you want to confirm if this empirical formula we have here is correct, so we use the valencies. So do we have a common factor here? Yes, 2. So 2 can divide here to get 1, and also here to get 1. So when we interchange the valencies, we are going to have magnesium 1 and oxygen 1. So you can see the formula for magnesium oxide is MgO. So meaning this is correct.